Alright, welcome to Earth Science. We're going to start getting into the 3 rock types one at a time. We're going to do igneous today, and then next week we'll do the other 2. So, igneous rocks. This reference table, you're going to use that a lot. Get that out and find it. Then I'm going to go back to these notes that we started the other day, and I'll scan and upload all this as well too. So igneous rocks, as hopefully you know by now, are rocks that come from cooling magma or lava. Alright, so magma is rock that's hot enough that it's a liquid. Like conceptually, the same idea that water is warm enough that it's a liquid, and if it cools enough, it turns to solid, like ice. Down here, same deal. Yes, that temperature is like way different, but down here we've got rock that's hot enough to be a liquid, and eventually it's going to cool enough that it will turn into a solid. Now the thing that's kind of hard to see is that in that liquid, that melted rock, like with water, it's H2O. You know what water is, right? But with rock, it's minerals. These are minerals that make up the igneous rocks right down here on the reference table. These are warm enough that they're in a liquid form, they're melted, and then as they cool, they begin to solidify and form bit by bit by bit, like molecule by molecule. They form on a really small scale. These look like crazy names. Don't worry about them so much yet. Maybe you've heard of quartz before. Quartz is one of the minerals that might be in an igneous rock. So, one of the big things with igneous rock, there's basically 2 big things, is that when this magma works its way to the surface, sometimes it doesn't make it all the way. It gets stuck within the earth. It's going to be insulated by the overriding layers of the earth. Sometimes it goes shooting right out of holes in the earth, like we call them volcanoes, right? Those you've probably heard of or seen pictures of. The giant difference to keep in mind here is that these, because they cool inside the earth and they're insulated, cool slowly. These, because they come popping out onto the surface of the earth, draw some arrows over here, that's an arrow, cool quickly. So, what does that mean? When these cool slowly, what's going to happen is that there's more time for these crystals to form. So if you've got some magma that has some quartz in it, if it comes squirting out of the earth over here in our volcanic session, then these quartz crystals don't have as much time to form. Whereas if it comes here into one of these, we call it a pluton, into one of these plutons, it's going to cool nice and slowly, which means that the quartz crystals have time to get larger and larger and larger. Basically, the relationship is the longer it takes to cool, the larger the crystals are going to be. So I'll put that in the notes over here, and I'll scan these and get them in there for you. These cool slowly, therefore have what we call a coarse texture. What that means is that there are large crystals. It's one of the things that's tricky. This coarse texture thing, people always want to think this means like that it feels rough, it feels coarse. That's not the case. It's how big are the crystals within it. If you take a coarse texture rock and polish it smooth, like some of you might have granite countertops, a granite countertop has a coarse texture. If you feel it, it feels perfectly smooth because we've polished it, right? Coarse refers to the size of the minerals, not the feeling of the rock. All right. The vocab word for these is intrusive. Inside the earth. All the opposite happens up here. These cool quickly. That's quite a cue right there. These cool quickly. The vocab word there is extrusive. They explode onto the surface of the earth. And you could potentially get a couple different textures with this. First, let's just do the opposite, of course. You can get fine textures. Basically, those minerals in this case are going to be, the crystals will be so small you can't really make them out with the naked eye. You can also get something, these 2 sound weird, but they're actually really easy to spot. You get one called vesicular, which means in the reference tables is going to hook you up with this. It has gas pockets. Or you can get one that's like glassy. A lot of people know what obsidian is. Looks like a hunk of glass, essentially. That can happen in these extrusive situations as well. All right, so those two are big, intrusive, extrusive. And if you've been playing with the reference tables and doing the activities from the last couple days, you might have seen those things on there already. So we got intrusive rocks here. So your intrusive rocks will be your granite, pegmatite, diorite, gabbro. I promise, I'm not going to give you these. I mean, you know, this is a whole at-home situation. I'll simplify your lives a little bit. We'll really just stick to the basics. Your extrusive rocks can basically be any of those guys. And then what they do over here is the texture matches. So it's like, hey, I can't remember all this stuff. Like I always say, intrusive rocks have either a very coarse or a coarse texture. Extrusive rocks have either a fine, a vesicular, or a glassy texture, and they even hook you up with the idea that vesicular means that there's gas pockets, so they make your life easy there. Now, I know there's a lot that are like combined and it gets a little bit weird, but don't panic. Again, I'm going to try to give you just the most basic questions I can, knowing that this whole at-home situation is a little tricky. All right. Next, that's about half of it, and I do recommend maybe rewatching this a time or two to make sure you got that down. That's like one of the two big things we got to do is the cooling history. Did it cool slowly or did it cool quickly? Next, what we got to do is the idea that these magmas are not uniform. They're not all the same everywhere on the planet. Depending on what's going on tectonically, there's going to be some differences. And those differences are all spelled out down here. This is what left to right is. So basically, the previous thing, the cooling history, is top to bottom. This next thing we're going to do, the composition, is left to right. So here's some of these crazy words, but again, it's more stuff you don't have to memorize if you can just use a reference table. And again, this my resolution wasn't so great on my printer here, but either way, let's circle this. Felsic is one endpoint of your compositions. This says rich in Si and Al, that's silica and aluminum. Those are the bottom of another reference table. I can show you that another time. But don't rack your brain. Rocks that are felsic have a density that is lower and have a color that is lighter. Going to the other end of the spectrum, we've got mafic, which are rich in Fe and Mg, which is iron and magnesium. And again, you don't have to memorize anything. It's all just sitting here. The density of mafic rocks is higher. The color of mafic rocks is darker. So really, this is a reasonably complicated reference table. This thing is a headache to look at. But when it comes down to it, it's not too bad because all you got to do is go left for light colored rocks, right for dark colored rocks, and then from bottom to top, it's going to be your coarse rocks down to less coarse, down to fine, and then getting up into the vesicular and glassy guys up here. All right. That should do it for now, I suppose. I'll put up some more stuff in the Google Classroom. Try that video a couple times. That was a lot that I just chucked at you. I'll scan both of these. Maybe I'll chuck a couple more notes on there before I scan them. And what I'd really like to do is get some pictures of rocks for you to play with online, see what they look like, and see if you can figure out a couple of these things, and do some regions questions. I'm thinking about doing a quiz by Friday. Other than that, happy weekend. So long. Good luck. Welcome to Earth Science.